Hello there. I am Syed Rahmath Ullah Hussaini, a second year student from Computer Science Engineering with Artificial Intelligence and Machine Learning department. This is a project presentation developed during my internship at Delloyd R&D Malaysia under the guidance of Dr. Ahmed Rimaz Faizabadi. Without further ado, let's move on to our very first project, Vehicle Attribute Identification and Scene Summary. We were given the task to develop a program to detect vehicle attributes such as type, class, color, make, and provide a scene summary with the following details. They are listed below. Number one, incoming traffic. The outgoing traffic, the total number of vehicles in the image. Last but not the least, these following details. To go more in depth on our objectives, we move on to our second slide. In modern smart cities, identifying vehicles such as type, color, make, and license plate plays a vital role in traffic management, law enforcement, and road safety. This project focuses on automating that process using deep learning and object detection, capable of understanding an entire scene, not just detecting vehicles. Get more in depth on the objectives. These are the following objectives: vehicle detection, as I said earlier, color detection of the vehicle, the model of the vehicle, the make, as you can see in the slide, and license plate detection. Just for reference, I have listed these objectives on the screen. Okay, we move on to the methodology. Let's look at the system workflow. The project was implemented using YOLO V8 and latest object detection model by Ultralytics. A custom dataset was prepared containing vehicle images and rated for vehicles, logos, and license plates, all configured in YOLO format via a data.yaml file. Model training was carried out on Google Colab using GPU acceleration with 60 epochs, batch size was 8, and input resolution was 640 by 640 pixels. The optimizer used was Adam W, with data augmentation techniques like mosaic and mix-up to improve generalization. What you see on the screen is my directory. To go more in depth, we move on to my VS Code. So this is my project directory. As you can see, it contains these folders. Q2 underscore results contains the annotated images. Vehicle underscore dataset contains the dataset which was provided to us, stored in this folder. If I can show you one of the images, yeah, this is how the dataset looks like. And I've used Makesense AI to create labels and then store it in this folder. Moving on, we have the data.yaml file which is created in our training script. This is my YOLO V8 training script where I've trained my model. We'll get back to this in a moment. This is the report page where I've created the report of my experiments. And check this out on my GitHub. This is the README file, and this contains all the requirements to run this program. As my PC is not equipped with a GPU, I have used Colab to train my YOLO V8 model. So this is my YOLO V8 training script. We'll be going through each cell. This program trains and tests a object detection model on a custom vehicle dataset containing cars, bikes, buses, license plates, and logos. Firstly, we import OS, which is for file and folder management, and find my folder path, dataset folder path, and store it into dataset underscore path variable. Over here, we install Ultralytics, which is a YOLO V8 library. YOLO V8 is short for You Only Look Once. And then we create a YAML file. This file tells YOLO what objects to detect and where the dataset is stored. Over here, we import OS, shuttle, and random. Shuttle is to copy and move images and label files, and random is for splitting dataset randomly into training and validation sets. And Ultralytics is to use YOLO V8 for object detection. This code organizes your dataset into YOLO format. This cell trains a YOLO V8 object detection model on a custom dataset of vehicles. Firstly, we import a YOLO class from Ultralytics library and load a pre-trained YOLO V8 medium model using this command. This model already knows the basic object features like the Coco dataset, so it can quickly adapt to vehicle images. Next, we train the model using our dataset configuration file data.yml, which we have created earlier. This defines the image paths and 14 object classes. We train for 60 epoch with a batch size of 8 and an image size of 640 by 640 pixels. The training uses the RMW optimizer, a learning rate of 0.001, and includes data augmentation like mosaic and mixup to improve generalization. This line runs the training on GPU if available. I've done the training on Google Colab. After training, the results, including the model weights, loss graphs, metrics, are automatically saved in the specified project folder. Then we evaluate the model on a validation dataset using metrics equals to model.value. This provides the accuracy and stores the precision, recall, and mean average precision. Finally, we test the trained model on a sample image using model.predict. Finally, we test the trained model on a sample image using model.predict. This performs inference, draws bounding boxes and around the detected objects, and saves the annotated image inside the folder. In summary, the script fine-tunes YOLO V8 on a custom vehicle dataset. And then we move on to the inference part. This Python script performs a vehicle attribute identification using a trained YOLO V8 model. Firstly, it automatically finds the latest best.pt model file and loads it for inference. Then it reads a test image and runs the YOLO model to detect multiple vehicle attributes such as vehicle type, color, logo, and license plate. The detections are categorized into vehicle plates and logos. The script then intelligently associates each license plate or logo with its corresponding vehicle using IOU position matching. It also estimates the vehicle color, direction, and lane position based on bounding box coordinates. Finally, the program draws colored bounding boxes and text labels on the image for visualization, saves both an annotated output image and a detailed JSON summary file describing each detected vehicle's attributes. In short, the script transforms raw ULO detections into structured human readable analysis for traffic, identifying vehicle type, brand, color, plate presence, direction, all in one step. After training my model, the results are stored in this Q2 underscore results folder. These are the annotated results. As you can see in the image, it correctly identifies the type of the vehicle car and the color, which lane it is driving on, right and left. Over here, it also calculates the number of vehicles present in this frame, incoming traffic, whether it has license plates. Well, it in this image it does not correctly identify the logo as it was run on 60 epochs. If it had run on higher epochs, it might have been more accurate. But in certain cases, it did over here it did identify the logo, license plate correctly, and it also identifies the class of the vehicle, truck. Let's look at some other cases. In this, it correctly identifies the logo of the vehicle, the license plate, the type, truck, the color, and in this case, even for a bike, it correctly identifies the vehicle type, vehicle class, the color, and the lane it's driving on. Let's look at some other images. This is an outgoing and incoming traffic. Yeah. So the results are stored over here. So I've also prepared a report based on my observations. You guys can check it out. Moving on to the next. So this is the next question that was given in our assignment. We were supposed to develop a program to detect faces and images, locate the tip of the nose and the center of the eyes, then annotate the images accordingly. So this is my project folder. This is my directory. This is the result folder, the test image I've used, the code, the report I've created, the README file, and the requirements to run this Python code. So we'll be having a quick look. So I'll be explaining this Python program that I've coded, which uses MediaPipe face mesh and OpenCV to detect facial landmarks such as the nose, tip, and eyes, and then annotate them on an image. This project can detect multiple faces, draw full facial mesh, and highlight key facial points. Firstly, we start off by importing these libraries. We import OpenCV, which is short for computer vision. It is used for reading, displaying, and annotating images. And then we import MediaPipe as MP for high accuracy facial landmark detection. We import NumPy for mathematical operation and OS for file operation. OS stands for operating systems. Nextly, we initialize the MediaPipe face mesh. These lines load the MediaPipe's face mesh module along with built-in drawing utilities and styles. Face mesh detects 468 facial landmarks per face with very high precision. These are predefined index values for importing important fa- These are predefined index values for important facial regions. MediaPipe assigns a unique ID to each landmark and points on the face. Here we use the index 1 for nose tip and these list of indices for the left and right eye. This is the function to compute eye centers. This helper function calculates the average XY position of all the landmarks from the eye. In short, it gives us the center points of the eye. This function, let me just scroll it a bit. Yeah, this function, the main point of this function is to read the input image, detect facial landmarks using MediaPipe, draw bounding boxes in facial meshes, and mark the nose and eyes with color-coded points and labels. We first load the image and convert it to BGR to RGB because MediaPipe expects RGB input. Then we pass it through a face mesh detector to identify all face landmarks. So this is an important line. For each detected face, we first draw the mesh connection using MediaPipe's default distillation style. Then we draw a green bounding box around the detected faces. Then we annotate the nose tip with a small red circle and labeled nose tip. Similarly, both eyes are located using landmark averages marked with blue circles and labeled as left and right eye. Then we save the annotated output. After processing, the annotated images is saved in the results folder so we can visually verify their detected points. And then the section loops for every image in the input folder, calls the function to detect the face landmarks, and saves the annotated results in a separate folder. In conclusion, this program detects multiple faces in an image, identifies key facial features like the nose and eyes, draws a face mesh overlay, and saves the annotated results with bounding boxes and labels. So this folder contains it. So this folder contains the test images that I've used. Firstly, this is Dr. Phil, a very famous American um, internet personality, and then I've used a picture of myself, and this these are the results. In this case, it has correctly identified the tip of the nose and the center of the eye of this famous figure. And in my case, it has also again correctly identified the tip of the nose and the center of my eyes. I've also created a report based on my observations. You guys can check out. Um, and yeah, that is it. Moving on to the next project. This is the next project which was given in our assignment. Face blurring in video feeds. We are to capture live video feed from a webcam or CCTV, detect and blur all faces in the feed, display the processed video feed, and add functionality to save video clip when required. So we move on to my project folder. This is my project folder. This is a directory. This is the results folder, the Python code, the report I've created, the README file. So I'll be explaining this Python program that I've coded. It uses OpenCV and MediaPipe to detect faces in real time from a webcam and apply a mosaic or pixelated blur effect on them. This program can also record the processed video when you press the R key and quit with Q. Let's break it down section by section. Firstly, we import these libraries, OpenCV. It is used for image processing and webcam input and drawing. MediaPipe is used for advanced machine learning based face detection. It was developed by Google. We import it as MP. Then we import NumPy as NP. It handles numerical operations. And then we import time, which is used to calculate frame rates, FPS in short. Then we initialize phase detection. Here we initialize the MediaPipe phase detection and its drawing utilities. As a backup, we also load a hard cascade classifier from OpenCV for older systems. This also ensures that if MediaPipe fails, the hard model can still detect faces. This line loads the MediaPipe phase detection model with a minimum confidence of 50%. Model underscore selection equals to 0 means that it's optimized for short range faces like in a webcam feed. This is the webcam setup. This opens the default webcam. If it fails, we exit with an error message. We also fetch the frame width, height, and frames per second to use later. This is the video recording setup. These lines prepare for saving the output video. The variable recording helps toggle between recording and pausing. This is a custom function apply. This is a custom function applies a mosaic or pixelated blur to a detected face region. It works by reducing the face image size and then scaling it back up, giving a pixelated look. This is the main loop for video processing. This loop continuously captures frames from the webcam. We first convert the frames to our RGB for MediaPipe, then we pass it to MediaPipe for face detection. If faces are detected, we loop through each detection and extract bounding box coordinates. We then blur the region using our mosaic function and draw a pink rectangle around the face. If MediaPipe does not detect any faces, we switch to hard cascade detector. This ensures the program can still work even if MediaPipe fails or runs slowly. These lines overlay the frames per second and other number of detected faces directly on the video feed. In short, it displays the info on screen. This is the recording control. When we press the R key, the code toggles between the start and stop recording. If recording is active, a red circle and the word rec appears on screen. And if we want to quit, we use the Q key. So pressing Q ends the loop and stops the program gracefully. Finally, after the loop ends, we release all resources, closing the webcam, video writer, and destroying all OpenCV windows. In conclusion, the script captures the live video feed, detects faces using MediaPipe or hard cascades, applies a mosaic blur effect to hide faces, displays FPS and face counts, and allows optional recording with a single key press. So when you run this Python program, the webcam opens and the when you record the video feed, it's stored as an AVI file, audio video input, and it's stored in my result folder. So I've taken screenshots from my video feed. So this is what it looks like. It captures my face, draws a bounding box, blurs my face, also gives me information like the FPS, number of faces. So that is the result for this program, and I've also created a report based on my observation. You guys can check out. Yeah, moving on to the next. The next few programs I'll be skipping as it's optional. So the next project that I've done is cats versus dog classification. We use an ImageNet pre-trained model to classify images of cats and dogs, collect 5 sample images where dogs are misclassified, and record and discuss the results. So this is my project folder containing these folders dataset which I've taken online, few images of cats and a few images of dogs which might have the possibility to be misclassified. The output is stored in the output folder. Uh, in this case, the results are stored in the result folder. This is the Python code. So I'll be explaining my Python program that uses TensorFlow and pre-trained MobileNet V2 model to classify images of dogs and cats. The program automatically analyzes each image in a folder and predicts what it is, simplifies the results, and saves annotated images with prediction labels. Firstly, we start off by importing these libraries. Here we import OS for handling file paths, NumPy for array and matrix operations, TensorFlow to load and use pre-trained deep learning model, CV2, OpenCV to draw and save annotated images. This is the folder setup. These lines define where the input images are stored and where we'll save the annotated results. If the output folder doesn't exist, it automatically creates one. This line loads the MobileNet V2 model pre-trained on ImageNet dataset, which can recognize over 1,000 everyday objects, including many dogs and cat breeds. This is a function which classifies this image. It resizes the image to 224 times 224 pixels. It converts into an array and pre-processes it for the model, runs predictions using models, and returns the top 3 predicted labels with confidence scores. And then we process all images. This loop goes through every image file in the input folder and classifies it. Then the model predicts very specific breeds like golden retriever or Siamese cat. Here we simplify those results. Any dog breed becomes simply dog, cat breed remains as they are, and anything else is labeled as other. Over here, we annotate and save the image. For each image, the predicted label and its simplified version are written on top of the image in red text. The annotated image is then saved to the results folder. This prints a clean summary table in the console showing the file name, the top predicted label, and its simplified result. This section specifically checks for cases where a dog image wasn't simplified to dog, basically identifying possible misclassification. And then we print the reason for inaccuracies. MobileNet V2 is trained to classify specific breeds, while our script only looks for general categories like dog or cat. So if the model predicts a very rare dog breed, not listed in our rules, it gets marked as other. That's why cats which have fewer variations are more often more accurate than dogs in the setup. In conclusion, this program uses a pre-trained MobileNet V2 model to classify animals, simplifies dog and cat breeds into broader categories, annotates and saves the output images, and prints a neat summary and misclassification report. It's a great example of transfer learning using large pre-trained model for a simple customized classification task. Let's look at some of the results that we have gotten. So in this case, the image of a cat was correctly identified, Persian cat. Another case, another case, tabby. Let's look at the cases where it misclassified the dogs. For example, in this case, it misclassified this dog as a wolf. In this case, it misclassified this dog as a golden retriever. In this case, it misclassified the dog as a tiger. And the output of this Python program was stored over here. So it prints a classification table, lists out all the image files, and gives the top one label, and also simplifies it. Over here, as you can see, it misclassified the dog breeds, and the reason for inaccuracies has also been predicted. So I've also made a report based on my observations, which you guys can check out. And yeah, that is it.